Hello friends, in this video we are going to study about the instrument Q meter, which is also known as the RLC meter. This is used for the measurement of inductance, resistance, capacitance and the quality factor of the coils. So in this video we are going to study about its working, principle of working, its construction and its applications. So let us start with our topic. The Q meter or the quality factor meter, it is an instrument which is used for the measurement of quality factor of coils and for the measurement of inductance, resistance, capacitance of the coils at the radio frequency. Now, as this Q meter or the quality factor meter, it is used for the measurement of inductance, capacitance and resistance. So it is measuring the L, C and R of an electric circuit. So it is also known as the RLC meter. Now, what is the quality factor of a coil? Quality factor is defined as the ratio of the inductive reactance to the effective resistance of the coil. Okay, so if we write its formula, it will be Q equals to ratio of inductive reactance to the effective resistance. So inductive reactance is XL and the effective resistance is R. Now we know that we are measuring the inductive reactance and the effective resistance at the radio frequencies. So XL will be equals to omega naught L upon R. So this is defined as the quality factor or the Q factor of a coil. Now this quality factor, it is also known as the storage factor. So if we are defining the storage factor of a coil, it will be Q equals to the power dissipated by the coil divided by the power stored in the coil. Okay, so if we want to find out the storage factor of any of the storage elements which are storing energy in them, like the inductors and the capacitors, so for them, if we are defining the storage factor or the quality factor or Q factor, it will be the power dissipated divided by the power stored in the element. So we can say that this storage factor, it is defining us the goodness of the coil or the performance of the coil. Okay, and we can say that it is a kind of figure of merit of a coil, that how good is the performance of the coil and how much energy the coil or the element can store in it. Okay. So this is about the quality factor. Now, while we are, as I've said, that this Q meter, which is the instrument used to measure the quality factor or Q factor of the coil. So this Q meter, it can measure the inductance, it can measure the capacitance, and it can measure the resistance of a electric circuit. So why, as I've said that it is measuring it at a radio frequency, so why we are not directly measuring it? The difference is that the effective resistance, the value of the effective resistance in a DC circuit and in an AC circuit, they are different. Okay, so if we are using the same circuit for measuring the resistance or effective resistance in an AC circuit and in a DC circuit, it will give a different value, because the value of the resistance, it depends upon the frequency in an AC circuit. So instead of directly measuring the effective resistance, we are measuring it indirectly by first determining the quality factor, and as the quality factor is equals to the ratio of the inductive reactance to the effective resistance, we can measure the effective resistance of an element or of a circuit. So this effective resistance, it is not measured directly. Instead of that, we are measuring it indirectly by first measuring the quality factor or the Q factor, and through that, because Q is equals to XL upon R, so through this we can measure the value of effective resistance as XL by Q. Okay. Now, this Q factor or the quality factor, it is used for the measurement of the Q. Okay, so let's see the principle of working of this Q meter or the RLC meter. So the principle of working of the Q meter, it is based upon the well-known characteristic of a series resonance circuit, which is having the R, L and C, which are connected in series with each other. So let's see the circuit through which we can understand the principle of working of the Q meter. Now this is the series resonance circuit in which we are having the resistance, inductance, inductor and a capacitor, which are connected in series with each other. Now this circuit is having the voltage supply, which is providing the voltage E to the circuit. The voltage drop across the resistance and the inductor, it is collectively called the EL, and the voltage drop across the capacitor, it is called EC. The current flowing in the circuit is the I naught. Now, this is a series resonance circuit. So at the resonance frequency, we have a condition that at resonant frequency F naught, we are having XC is equals to XL. This is the condition for a series resonance circuit, that at the resonant frequency, the inductive reactance and the capacitive reactance, they are equal to each other. Okay. Now we know that the value of Xc is what? 1 upon 2 pi F naught C, and the value of XL is 2 pi F naught L. So if we put the value of Xc and XL in this equation, where F naught is our resonant frequency, we will get XL is equals to Xc. So 2 pi F naught L will be equal to 1 upon 2 pi F naught C. Okay. So F naught square will be equals to 1 upon 4 pi square L C. So if we find out F naught, it will be 1 upon 2 pi under root of LC. So this is the value of the resonant frequency. Okay. Now if we draw the phasor diagram for this circuit, so we know that the voltage drop across the resistance and the current, they are in same phase with each other. If we are talking about an inductor, so voltage is going to lead the current by 90 degree, and in the case of capacitor, the voltage is going to lag the current by 90 degree. So we'll draw the phasor diagram, which is showing the relationship between the voltage drop across each of the elements and the current flowing through them. So if we take the current as our reference phasor, which is I naught. So if we are talking about the resistance, the voltage drop, that is I naught R, will be in same phase with each other. If we are talking about the inductor, so voltage is going to lead the current by 90 degree. So it will be I naught XL across the inductor. And if we are talking about the capacitor, voltage is going to lag the current by 90 degrees, so it is I naught XC. Now we know that the sum of the voltage drop across the resistance and inductor, collectively their sum is EL. So I naught R and I naught XL, if we extend them, their resultant will be the EL. Okay. So this is our input voltage. Our input voltage is what? E, and this input voltage is equal to the voltage drop across the resistance. Now here the inductor is also present and capacitor is also present. So input voltage is measured across the resistance and output voltage is measured across the capacitor. So this I naught R, which is the voltage drop across the resistance, it will be equal to our input voltage E. So this is the phasor diagram of the Q meter. Now, as we have got the value of the resonant frequency and we know that the input voltage is E and output voltage is the voltage across the capacitor, that is EC. Now the current at resonance, it will be I naught and this I naught is equals to the voltage across the input voltage, that is E divided by the R. Okay. Now through this equation we can get the value of the input voltage. Input voltage is E, so E will be equals to I naught into R. So here we have got the input voltage. Now if we get the ratio of the input voltage and the output voltage, it will be equals to EC is our output voltage and input voltage is E. So it will be equals to EC is the voltage across the capacitor. So it will be equal to I naught XC, and E is the voltage across the resistance which we have calculated I naught R. Now at resonance frequency, we know that XC is equals to XL. So here we can write it as I naught XL upon R. So it will be equals to I naught. What is the value of XL? Omega naught L upon, here we are having I naught R. Okay. So we will write it as I naught R. Now I naught and I naught, they will be cancelled. So the ratio of the output voltage upon the input voltage, it is equals to omega naught L by R. Now we know that what is our quality factor? We know that quality factor Q is defined as the ratio of the inductive reactance to the effective resistance. Inductive reactance is omega naught L upon R. And here we have got the ratio of EC upon E as omega naught L by R. So we can say that EC upon E is equals to the quality factor Q. Or we can say our output voltage EC is equals to Q times E. Now this was the voltage across the capacitor, and voltage across capacitor is our output voltage. So we can replace this by E naught, which is the output voltage, and it is equal to QE. So this relationship says that the output voltage, it is Q times the input voltage. So if we keep the input voltage as constant, we can directly read the value of the quality factor from the output voltage, or we can say that we can, if we are measuring the voltage across the capacitor, so that will be directly equal to the value of the quality factor of the circuit. Okay, so this is the principle of working of the instrument Q meter. So we can say that the input voltage, it is magnified Q times, and if this output voltage, we know that it is the voltage across the capacitor. So if we are connecting a voltmeter across the capacitor, so that voltmeter is going to give us the reading of the capacitor voltage, or we can say the output voltage. So we can, if this input voltage is kept as constant, so the voltmeter, it is going to give us the reading, which is the reading of the quality factor of the coil. Okay. So this is the principle which is used in the Q meter or the RLC meter. So let's see the construction or the circuit of the Q meter instrument. So this is the circuit diagram for the Q meter. In this Q meter, there are various components, like it is having a variable RF oscillator, a very low value of a shunt resistance. Here we are having a thermocouple voltmeter, and the coil under test, the coil whose quality factor or the resistance inductance we want to measure, that coil under test is connected between the terminals T1 and T2, and between the terminals T3 and T4 a variable standard capacitor is connected, and electronic voltmeter is connected across this capacitor, which is going to measure the capacitor voltage. So the principle is same, that we are having a series resonance circuit RLC, and in this series resonance circuit we are measuring the voltage, the output voltage, the voltage across the capacitor, and that voltage will be E naught will be equals to Q times of the input voltage, and input voltage is this E. Okay, and this EMF or the this input voltage is induced due to this shunt resistance. So if we talk about the components of the Q meter, we will be having a variable RF oscillator, variable radio frequency oscillator. Then we will be having two voltmeters, a thermocouple voltmeter and an electronic voltmeter. Then we are having a shunt resistance, and the value of this shunt resistance is very low. Means that it is of the order of hundreds of the ohm, or we can say it is approximately 0.02 ohms. So as the value of this shunt resistance, shunt means it is connected in parallel with the circuit. So the value of this shunt resistance is very low. So this is hardly going to introduce any resistance in the circuit. Okay, but due to this shunt resistance, an EMF E is induced in the circuit, and this EMF E is measured through this thermocouple voltmeter. Okay, so this EMF E is our input voltage, and this input voltage is going to cause a current to flow in the circuit, and due to that current at the radio frequency, this series resonance circuit will be resonating, and we will be having XL is equals to XC. We are going to adjust the frequency through this variable RF oscillator. The frequency is adjusted so that we are getting this condition XL equals to XC. Because at this resonant frequency only we are going to get this condition that E0 is equals to QE. Okay. Now, because we are having the output voltage connected across, we have to measure the output voltage across this capacitor. So we are going to calibrate this electronic voltmeter such that it is going to give us directly the readings of the quality factor or the Q factor of the coil. So if we talk about the measurement of the quality factor or Q meter, what will be the steps for that? First, the RF oscillator, it will be adjusted at the desired frequency, and the tuning capacitor, it is adjusted for the maximum value of the output voltage. So first step will be to oscillator is set to the desired frequency. Second step is tuning capacitor. Now under resonance condition, we will be having Q E0 will be equals to Q times of E, that is output voltage is equals to Q times of the input voltage. So the voltmeter across capacitor. Value of the Q factor directly. As we are reading the value of the Q factor directly from the instrument, so this Q meter is also known as the direct reading instrument. Okay, so this is the measurement of the Q factor through the Q meter. Now in this circuit, when the measured value of the Q, it is different from the true value, there will be an error due to the distributed capacitance of the coil and due to this shunt resistance. So corrections has to be made due to this shunt resistance, for this shunt resistance and for this distributed capacitance. So we can say that the measured value of the Q factor from this Q meter, it is less than the true value of the quality factor. Now, why this is occurring, why the measured value is different from the true value? Because the Q which we are measuring from the instrument, that is regarded as the Q or the quality factor of the complete or the whole circuit. But we only want to measure the quality factor of the coil. Okay, so that is why there is a difference between the measured value and the true value, and there is an error in the instrument, and this error has occurred due to the shunt resistance and the distributed capacitance of the coil. So corrections are made for the shunt resistance also and for the distributed capacitance. So first we will see the correction for the shunt resistance. Because shunt resistance is also connected in series with the RLC circuit, so this shunt resistance will also be added in the effective resistance of the coil. So as we know that the quality factor, it is a ratio of the inductive reactance, that is omega naught L upon the effective resistance. So the shunt resistance is also added in it, so it will be R plus RSH. Okay, because here as a when we have studied this circuit, we have told that this shunt resistance is very low, but if the value of this shunt resistance is comparable to the effective resistance, it is going to affect the readings. Okay, so RSH is also added in the effective resistance, so the measured value of the Q is omega naught L upon R plus RSH, but true value is omega naught L by R. So if we calculate the error, that is the difference between the true value and the measured value, we will see that the true value is equal to the measured value multiplied with 1 plus RSH by R. Okay, so we can say that the measured value, it is smaller than the true value by this factor 1 plus RSH by R, and so there is a difference between them and an error has occurred. Now, if we are measuring the coils which are having very high resistance, or we can say very low value of the quality factor, then this difference between the measured value and the true value, it is negligible. So we can use this Q meter for the measurement of the coils which are having very low value of the quality factor. So if we are having quality factor as very low, means we are using is for low Q coils. But if we are using the same instrument for high Q coils, the error will be more. Now, next correction will be the correction for the distributed capacitance. Now, in this circuit, you have seen that across this the coil which is under test, we have connected it between the terminals T1 and T2, and it is having a distributed capacitance also related to it. So as in the diagram, the circuit diagram of the Q meter, we have seen that the coil under test is connected between the terminals T1 and T2, and this coil is also having a distributed capacitance. Some capacitance will also be there in the coil. So this capacitance is going to be added with the value of the capacitor. Okay, so the measured value of the quality factor or the Q factor, it will be smaller than the true value. Okay. So the measured value is less than the true value by a factor which depends upon the value of the distributed capacitance. So we know that the true value is XL upon R. Okay, and at resonance frequency XL is equals to XC. Okay, now measured value will be equals to the XC plus the distributed capacitance CD. So we can say XCD, okay, upon R. So if we see, the true value is equal to the measured value 1 plus CD by C. So we can say that the measured value is smaller than the true value by a factor 1 plus CD by C. And this factor, it depends upon the value of the distributed capacitance. So these are the two corrections which are made in the readings of the Q meter. First correction was due to the shunt resistance and second correction is for the distributed capacitance. Now this Q meter, it is available in two forms. One is the series connection and second is the parallel connection. So in the series connection, the L, R and the coil, they are connected in series with each other, and in the parallel, so in the parallel connection, you can see that R and L and the coil whose resistance and inductance we want to measure, they are connected in parallel with each other. Means we are having a parallel resonance circuit and here we are having a series resonant circuit. Okay. Now if we come up to the applications of the Q meter. So this Q meter can be used for the measurement of various quantities, like it can measure the quality factor of the coil, it can measure the effective resistance, the inductance, capacitance, and also it can measure the bandwidth and frequency can be measured through it. So let's see that how this Q meter, it is measuring the different quantities. So first application is the measurement of Q, that is quality factor, which we have already seen that through the circuit how it is measuring the Q meter, how the output voltage, value of the output voltage, it is equal to the quality factor. So in this, how this quality factor is measured, E naught output voltage, it is equal to Q times of the input voltage, or we can say Q is equal to the ratio of the output voltage and the input voltage. And the same circuit as we have studied that in the Q meter, that is used for the measurement of Q. Second is the measurement of inductance. Now, as we know that in the resonance circuit, XL is equals to XC, and we were getting the resonant frequency as 1 upon 2 pi under root of LC. So if we take square of these, we will get F naught square is equals to 1 upon 4 pi square LC. So through this equation, we can get the value of the inductance L as 1 upon 4 pi square F naught square C. So through this formula, we can measure the inductance also. Now next is the measurement of capacitance. Now we know that we are having the frequency, we know the value of the frequency, resonant frequency, it is equals to 1 upon 2 pi under root of LC. So for the measurement of self-capacitance, what we do, we make two measurements. One is as frequency F1 and second at the frequency F2, such that the second frequency F2, it is twice of F1. Okay, this is the relationship between them. So if we talk about F1, its value will be 1 upon 2 pi under root of L C1 plus CD. Due to the distributed capacitance, this distributed capacitance will be added in the value of the capacitance of the coil. And if we talk about F2, it will be 1 upon 2 pi under root of L C2 plus CD. Okay. Now we know that the relationship between F2 and F1 is that F2 is twice of F1. So just put the value of F2, it is 1 upon 2 pi under root of L C2 plus CD is equals to 2 into 1 upon 2 pi under root of L C1 plus CD. So through this, we will get the value of the distributed capacitance as C1 minus 4C2 by 3. So this is the value of the self-capacitance. So we can say the distributed capacitance, which can be measured through the Q meter, because through Q meter we are getting the value of the resonant frequency, and we have used the condition, we have made two measurements at the different frequencies F1 and F2 such that F2 is equals to twice of F1. Now the next quantity which can be measured through the Q meter is bandwidth. Can also be measured in the same way that we are measuring the capacitance. We will take the values at the different frequencies, and through that we will get the relationship between the Q factor and the bandwidth as omega naught upon omega 1 minus omega 2. This is the relationship. Q factor we can measure through the Q meter. Omega naught is the resonant frequency, and omega 1 and omega 2 are the frequencies where the different measurements are taken. So through this formula we can measure the bandwidth. We can say omega 1 minus omega 2 is the bandwidth only, because bandwidth is the range of frequencies. Okay, so omega 2 is our higher frequency and omega 1 is our lower frequency. So if we are measuring the difference between them, we can measure the bandwidth through them. Next is the measurement of the resistance. So how we can measure the resistance? We are measuring the quality factor through the Q meter. So we know that the measured value of the quality factor is equals to omega naught L by R. Now L, we already know that L we can measure through by the formula 1 upon 4 pi square F naught square C. So the value of L is known, omega naught we know that it is equals to 2 pi F naught. So the value of R will be 2 pi F naught L upon the measured value of the quality factor. So through this we can measure the resistance of the coil. Next is measurement of capacitance. Now for the measurement of capacitance, we are going to use a dummy coil, and this dummy coil is connected between the terminals T1 and T2. Okay. Under T1 and T2, we were connecting the coil under the test. Now here we are connecting a dummy coil, and we are going to vary the value of the tuning capacitor. Suppose that we are getting the value of the tuning capacitor, we are varying its value, tuning capacitor, so that the resonant frequency is obtained, the circuit is resonated, and the value of the capacitor or the tuning capacitor we are getting as C1. Now again we are going to remove this dummy coil, and we are going to connect our coil under test, and the capacitor whose value we want to measure, it is connected across the terminals T3 and T4. Now this capacitor will be in parallel with the tuning capacitor, and suppose that again we are resonating the circuit, we are varying the value of the tuning capacitor, and now its value is C2. Okay, so in the second case, this was the first case, and in the second case we are connecting the capacitor which we want to measure across the tuning capacitor. So they are connected in parallel with each other, and this is our second reading, C2. So our the value of the capacitance which we want to measure, it is the difference between the two readings C2 and C1. Because in the first reading we are taking only the tuning capacitor, and in the second case we are taking both tuning capacitor and the terminal capacitor or the capacitor we want to measure capacitor under test. Okay, so the value of CT will be C2 minus C1, the difference between the two readings. Now other than these quantities, the other applications of the Q meter are like we can measure the frequency through it. Like F naught is equals to 1 upon 2 pi under root of LC. Through this formula we can measure the frequency also. Also unknown impedance can be measured. And another application is the characteristic impedance of a transmission line. So these are all the applications of the Q meter. So here in this video we studied about that what is a Q meter, why it is known as Q meter and RLC meter, what is the principle of working of this instrument, and then we studied that what are the quantities which can be measured through this Q meter, and in the last we studied its applications in different areas. So I hope that this topic Q meter is now clear to you. Thank you.